Let's consider a space where there are capital N number of particles and this number is constant. And let's assume that we are in this kind of volume. You have to think of this as a three-dimensional volume, and we subdivide this three-dimensional volume into L subspaces. So some portion of this volume will contain, let's say, n sub 1 particles. Another portion will contain n sub 2 particles, and all in all we have L of such subspaces. So for example, this subspace contains nl particle. So capital N will be given by n1 plus n2 plus n3 dot 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 plus nl. And now let's assume that we have a probability equal to 1 over L to find n1 particles in this subspace. We have a probability 1 over L to find n2 particles in this subspace, and so on and so forth. So there is some kind of homogeneity in the probabilities. If we want to find the total probability, W, and what is this total probability? This represents the probability that N1 states are in G1, N2 states are in G2, N3 states are in G3, dot dot dot, NL states are in GL. So this will be given by a product. We have 1 over L for the first state, and we have to be careful here, and we have to consider the number of arrangements of N1 particles, because different particles can enter this state. They are N1, but we can choose N1 particles from capital N in different ways. And what are the number of different possibilities that we have? Well, it's given by the binomial coefficient capital N choose N1. And what about the second substate N2? We have 1 over L, and in this case we can choose from N minus N1 particles, because we have already chosen N1 particles for the first state, and we have to choose N2 of those. So you get the idea. Then we have 1 over L times N minus N1 minus N2, and we have to consider the binomial coefficient N minus N1 minus N2, choose N3, dot dot dot, and then for the final state we have a similar trick here. We have a similar thing to consider. We have N minus N1 minus N2, dot dot dot, minus NL minus 1, but of course we will have to choose from NL, because capital N minus N1 minus N2 dot 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 minus NL minus 1 is equal to NL, and of course here we have to put NL like this. And so this gives us 1 over L to the power L, because we have L of such states. And then we have this first binomial coefficient is n factorial divided by n minus n1 factorial times n1 factorial here in the denominator. Then we have the second one, which is n minus n1 factorial divided by n minus n1 minus n2 factorial, n2 factorial here. Then we have this third one, n minus n1 minus n2 factorial divided by n minus n1 minus n2 minus n3 factorial, n3 factorial, and you get the idea. Okay, I will not write more terms, but you can see that these terms cancel, this one and this one, and this one with this one, and also this one will cancel with someone here. So the formula simplifies, because in this case you can write 1 over L to the power L, and then here you have n factorial divided by n1 factorial, n2 factorial, dot dot dot, nl factorial, like this. Now we will assume that n is a very large number, and so we can use Stirling formula, Stirling approximation. And you have 1 over L to the power L. N factorial can be rewritten as n to the power n times e to the minus capital N, like this. You also have a factor sometimes here which multiplies these two, but it's easy to understand that that factor can be neglected because the preponderant or the most relevant terms are these two. So we apply the same formula to n1 factorial here, which is n1 to the power n1 e to the minus n1. Then we have n2 to the power n2 e to the minus n2 dot 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 nl to the power nl e to the minus nl, like this. And if you put these results together, in particular if you put these exponentials together in the denominator, you will see that altogether that we cancel this term in the numerator. So if you put the exponentials together in the denominator, we get an exponential e to the minus n1 plus n2 dot 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 plus nl. So this will be capital N, and you see that this one cancels this one. And therefore, we are left with 1 over L to the power L, n to the power n divided by n1 to the power n1 dot 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 nl to the power nl. Now, if we consider the logarithm of w, which is a probability, this will be equal to, in the limit as n is very large, minus L natural log L, and then we have plus n log n minus sum over j of nj log nj. Now, these terms here are just a constant because, as I said, we have to consider n as fixed. L is a probability, so that's also fixed. And now, when n is very large, in particular, if we are considering a very large number of substates, where L is also very large, then this summation here can be considered almost coincident with an integral, and therefore log w can also be written as a constant minus integral n log n, and in this case we have to integrate over the volume element of the subspace Gj, and since we are considering the space of states, the volume element will be given by the state variables. So we have dp1 dot 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 dph, where h is a number related to the number of particles. In general, if we use positions x, so we have dx1 dot 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 dx3n, capital N. So we have 3n positions because we have 3 coordinates for each particle, and then we also have momenta, which I can call q, so q1 dot 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 dq3n. So as you can see, we have 3n coordinates for position and 3n coordinates for momentum, as you can see here. So this h would be 6n, for example, but that's not really important. It is just for the sake of convenience and so that I can avoid writing all these differentials. I will just write h differentials like this, just for the sake of convenience. But anyway, we can also write the total energy E of our system of capital N particles as given by integral of the energy per particle that I will call epsilon, then we multiply by the number of particles n, and we integrate over dp1 dot 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 dph. The total number of particles can also be written in a similar form as integral over the number of particles dp1 dot 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 dph. So this formula here is the generalization of the discrete formula n equal to the sum over j of nj, whereas this one here is the continuous version of this discrete version, E equal sum over j of epsilon j times nj, like this, where nj is the number of particles contained in the jth subsystem. And these two formulas, this one and this one, are constraints for this formula here. So if you want to maximize the probability W, and if we maximize this probability, it means that we are in a greater state of disorder, because this probability is related to the number of states, how many arrangements we have, how many combinations we have. So that's why we have to maximize logarithm of W by using these constraints, because that will lead us to the entropy. I will define the function f as logarithm of W. Then if I want to use Lagrange multipliers, I will have a constant that I will call minus alpha. I will put this constraint first, which is minus n plus integral n dp1 dot 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 dph, and I will have another constraint minus beta related to the energy. So I will have minus total energy plus integral epsilon and dp1 dot 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 dph, like this. And I also have to replace the expression for L and W here, and in particular I am interested in this part of the expression because this is just a constant. I'm not really interested in the constant since we have to take the derivative of f. So I can simply cancel this one here, and also let me move f to the left. F equal to, we have minus integral n log n dp1 dot 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 dph. Now what we have to do is we have to consider the derivative of f with respect to n and set it equal to 0. So we have derivative with respect to n of minus n log n. This is a constant term, and then we have minus alpha, derivative of n with respect to n, which is 1. Then we have minus beta epsilon, because we have to take the derivative of n with respect to n here. And we have to set this equal to 0, like this. And what we have is minus log n, then we get minus 1 minus alpha minus beta epsilon equal to 0, like this. From here we get n equal to e to the minus 1 minus alpha minus beta epsilon. Now, if we use this result and we replace it in the definition for L and W here, we get a constant. I'm not going to rewrite the constant. I have L and W equal to this integral here minus integral n, which is equal to this, and then I have log n, which is equal to the argument of the logarithm. So here we get minus 1 minus alpha minus beta epsilon times e to the minus 1 minus alpha minus beta epsilon dp1 dot 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 dph, and this minus becomes plus with all these minus signs here, like this. And from here we can rewrite this as 1 plus alpha integral e to the minus 1 plus alpha plus beta epsilon dp1 dot 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 dph. Then I get plus integral beta epsilon e to the minus 1 plus alpha plus beta epsilon, and then I have dp1 dot dph. In this case, I have not put epsilon out of the integral since this energy here can depend on these variables, whereas 1 plus alpha here is just a constant. And also beta is a constant, so I could put it out of the integral, but I cannot put in general epsilon. And how can I rewrite this expression? Well, also consider this formula here, this one, and also this formula here. When I replace the expression that we found for n, I have e equal to integral epsilon. Here I have e to the minus 1 plus alpha plus beta epsilon dp1 dot dph. Whereas here I have capital N equal to integral, and here I have e to the minus 1 plus alpha plus beta epsilon dp1 dot dph, like this. So here below, this expression here is just simply beta times capital E, whereas this expression here is simply capital N. So now let's do one more step. I can take the differential of the logarithm of w, and we know that n is a constant in our considerations. So I can rewrite this as beta, which is a constant, times the differential of E. And remember that for a system of particles where the number of particles is fixed, the differential dE can be written as the temperature times the differential of the entropy. In this particular case where I'm considering the number of particles fixed and also the volume of our system to be fixed. So in this case, I can rewrite dE as TdS. And this basically means that beta times T should be a constant, and therefore the logarithm of W will be equal to a constant, to this constant times the entropy S. And this constant is beta times T. And as you can see from here, since logarithm of W is dimensionless, because W is a probability after all, so ln W is dimensionless. S is entropy, therefore constant here should be 1 over entropy. And a constant in physics which is related to entropy is the Boltzmann constant. So this is 1 over Boltzmann constant, Kb. Therefore we can rewrite the entropy as K Boltzmann times logarithm of W, like this, which means that beta is equal to 1 over K Boltzmann times T. So the expression for the energy, the total energy E, should be written as integral the energy of the single particle times exponential to the minus, and here we have, remember, we have 1 plus alpha plus beta epsilon, so we have epsilon over K Boltzmann T, and we also have 1 plus alpha, and let me rewrite it like this, so I'm going to cancel these parentheses. Here I can rewrite it as e to the minus, and that's just a constant, so I have outside the integral I can rewrite e to the minus 1 plus alpha, like this, but this is not a constant because we have epsilon, and we have to integrate over the state variables dp1 dot dph, and the total number of particles is given by the integral of e to the minus epsilon over k Boltzmann T dp1 dot dph times e to the minus 1 plus alpha. So if I divide these two formulas, we get the average energy per particle. E over n is the average energy per particle, and we can calculate it using this integral epsilon e to the minus e over k Boltzmann T dp1 dot dph, and then we divide this by integral e to the minus epsilon over k Boltzmann T dp1 dot dph. These two constants will cancel when I take the ratio. So this is an important formula because it tells us how we can calculate in statistical mechanics the average energy of one particle. It's a formula that can be generalized also for quantum systems or discrete systems. In quantum mechanics, Planck used the trick where he discretized this formula, so we can do a similar derivation with the discrete formula, so starting from this expression here and taking the derivative with respect to nj instead of n, assuming that we have a continuous system. In this case, we have assumed that we have a continuous system, but we started from a discrete system after all, so it would be more natural to derive a similar expression for a discrete system. And in that case, you will get something like this. Average energy equal to the summation over j of epsilon j e to the minus epsilon j over k b t, and then we divide by sum over j of e to the minus epsilon j over k Boltzmann t, like this. It's as simple as that. But Planck used this formula in conjunction with the fact that the energy epsilon j for a photon was proportional to the frequency, he managed to derive the law pertaining to black body radiation.